Okay, so the problem says something about a vector going 1,000 meters north, this is number 17, and 2,300 meters west of north at a 35-degree angle. So I'm going to draw that with the blue pen. This is the main vectors. So I'm going to do 1,000 meters here and label that A. And then from that tip, because vectors are always joined tail to tip, or tip to tail, 2,300 meters west of north. Oops. So when it says west of north, it's saying that starting from the north axis, that's the y-axis, you're going to go 35 degrees that way, to the west. So that's going to be this angle here, 35 degrees. And this is 2,300 meters, and that's B. So we're going to break it down into components. A is a straight line, so it has two components. Every vector has two components. But in this case, A does not have, it has a x vector component of 0 meters because there's no horizontal tilt to this, it's just straight. And then it has a vertical or Vy component of 1,000 meters. So that's pretty simple, that's easy, whatever. The problem comes when we're doing vector B, because I'm going to redraw that vector here. So this is the hypotenuse of a triangle, and this is the y component. Oops. So the y component, and this is the x component. And our angle is 35. So if you notice here, what you notice is that we have a right triangle right here, which means we can use trigonometry. So let's do 2,300. So what we're going to do, we're going to say B. We're going to have Vx be equal to this vector here. I don't know if you can see here. This vector here. And that, we're going to use trigonometry there so we can see 35 degrees is opposite from what we want, and the hypotenuse is known, so we're going to use sine. So to find Vx, we're going to do, I'm trouble showing you this here. We're going to do sine of 35 is equal to opposite, which is unknown, so we're going to do that's the value of Vx, over the hypotenuse 2,300. And when you put that in a calculator, you're going to get about, let's see what I had, 1319 meters. 1,319 meters. For Vy, we're going to do the same thing, but since we're solving for this here, the adjacent to this angle, we're going to use cosine. And we have here a value, when you put it in the calculator, of 1884, so 1,884 meters. So we have our new, of the resultant vector, and let me draw that up here. Now I'm going to write VR for that one. We have the value of our resultant vector, the components of our resultant vector. I wrote Vy here by accident, sorry. There. So this resultant vector has a x component, which is the distance that goes horizontally of 1,000 meters. Oh, that is right. I'm sorry. Okay. It has a horizontal. Oh God. Okay. So Vx is, scratch that. I'm just gonna do this. So I'll show you how to do it with a triangle. So I'm gonna draw out the resultant vector here, VR. Vector. So then we're going to draw the components, and we know the length of these components because we calculated them here. So the total change in y for this vector, this resultant vector, is going to be the sum of Vy for B and Vy for A. So basically, the resultant vector's y component is the sum of the these vectors that we're adding, their y components. So this is going to be 1000 plus 1884 equals 2884. And the same thing for this horizontal. This horizontal one is going to be 0, right? You have a 0 up here, plus 1319. And that's going to just be 1319 meters. So this is where we can see how this is all coming together, because this reflects that there's no change in x with our first a vector, but there is at this b vector at an angle. So next we can just use the Pythagorean theorem to solve for VR's magnitude. And if it's okay, I'm just going to clear up, if I can find my eraser. I'm going to clear up some space up here to do that calculation. So we're going to do VR, the magnitude, is equal to the square root, right, the Pythagorean theorem, of 1319 meters, that's our x, plus 2884, our y. When you put that in a calculator, you're going to get a value of 3,171 meters. Now you're probably wondering, so this is our magnitude here, but how do we find the direction? And to do that, we're going to use an arc function. We're going to use an arc function to find the value of our resultant angle here. And you might be wondering, how do I know to use this angle? And the answer is you don't really have to use that angle if you don't want to, but because the problem specifies that we're going to be using an angle west of north, it's better to keep it consistent. You could choose to do this one. You can't choose this one because this is a right angle. That wouldn't make any sense. But you could choose this one if you wish. We're not going to do that right now. So to find this, and this is going to be west of north again because we're going up. We're going over from our north axis. So we're going to use a trigonometric function that can include the values we know. We know all three sides of the triangle, but because we used our calculation, we already calculated these values, we may as well use these. So I'm going to show you how to use it. I'm going to show you how to do it with the arctangent function. So we know that tangent of theta is equal to the opposite, which is 1319, over the adjacent, which is 2884. When you put that in a calculator, and make sure you're using degrees because the problem gave the value to us in degrees, we're going to get about 25 degrees. And again, that's going to be west of north. So that's your answer. That was number 17. Now, we're going to go ahead and look at 13b, and it's much simpler because in this case, we had a vector that was going at an angle, which meant that we had to recalculate our component vectors for this b vector that was going at an angle using trigonometry, which kind of added an extra step to the problem. And so I think one of the points of confusion for this number 13 that a lot of people have, and a lot of people have asked me about this problem, is what the component method is. And the component method is just what we use right now. We broke down our vector, so let's suppose we have this vector here, into two components, an x component and a y component. And keep in mind, these are both vectors in their own right. They have a direction. This one's going east, this one's going north. But they make up a greater part. These two are parts of this vector. This vector travels at this horizontal and up this vertical. So that's the component method. And on number 13, there was also the graphical method. And on the graphical method, you were supposed to do something with the grid. You were supposed to specify a scale for the grid and then count squares on the grid. That's not what we're going to do now. Now we're going to do the component method, which is going to give us a more accurate mathematical result, while the graphical method will give you more of an estimate. So we have a 12-mile horizontal and a 25-mile vertical. So you're going to try to draw it to the scale. I'm going to actually do a different color for that. We're going to try to draw it to the scale of the problem. So I'm not going to draw an axis on this one. So we're going to have the 12-mile horizontal and the 25-mile vertical distance. and we're trying to find the angle and magnitude of the resultant vector. That is to say, the distance between his starting point and ending point. So to do that, we're going to try to find the value of the magnitude. So to do that, we can just use the Pythagorean theorem. It's much more simple than the last one because our component vectors are the vectors that we're given are the component vectors of the resultant vector. Notice this is the horizontal component and this is the vertical component. So the resultant vector, Pythagorean theorem, 12 squared plus 25 squared. And that's going to give us, when we plug it into a calculator, a value of about 27.7 miles, which matches with the graphical method that you did that sent me. But I'm pretty sure you must have did the Pythagorean theorem for the graphical method, whereas you were supposed to count the squares. Now, I made a mistake when I sent to you the paper with my work example. I accidentally used an angle here, but you should be using it here because we're going to use it from the starting point. So to do this now, we're going to do the same thing we did before. We have the values of all three, but because we were given 25 and 12, to minimize error, we're going to use the tangent function so we can use these two values that we were given. So the tangent of theta is equal to the opposite over the adjacent. When you put that in a calculator, I don't know what you get because I made a mistake on my paper, but it should be the right answer. Make sure you're using degrees again. So yeah, that's about it. That's the component method in two different examples, 13b with just the components given, and with 17 when it gives you a vector with its own components to add. So summary, when you're adding two vectors, you're going to try, if it's giving you the components of them, you're just going to use the Pythagorean theorem. If it's given a vector that has an angle to it, you have to find the components of that vector and add them to the other components. You always add like components together. You always add the x components together and the y components together separately. And then you put them together using the Pythagorean theorem. To find the angle, you do this procedure again. So if you have any questions, message me again, but I am hopefully this explained everything to you.